사이즈 컨트롤도 그걸로 하거든요. G죠. 이제 그게 다른 안. TG의 가장 기본적인 기능이 면역 세포. 예전에 PG가 TV를 엄청 많이 쓰더라고요. 유경증 TV를 많이 쓰는 것 같습니다. Thank you. Hello again.
Hey,
Thank you.
all good? Do we
Yeah.
want to wait for Robin, or should we get started?
Yes. We need to wait 2 more people.
Sounds good. Is it clear so far for you guys, or do you have any questions? Anything I can clarify? Anything anything I can help with?
So far, we don't have some questions about because
Okay.
especially these two guys is specialized for the biological. So yeah, they are very the two guys are very professional. Yeah.
I have no doubt. Okay, sounds good. Yeah, I keep it very high level, so very simple. But again, I can really, if you have any questions, we can go in more details. And overall, my main takeaway is if you have any questions,
Okay.
come back to me. Okay, at any time, I'm very happy to help. Okay. But one of the things maybe I can show you, and that can be helpful here, is I have shared with you this folder. I don't know if you've seen it, but basically, hold on. So basically, I have shared this folder with you, okay, with different elements. And in here, there is the sales pitch. And in the sales pitch, if you open the sales pitch here, basically what we do is that we have the sales pitch for the, give it 1 second. We basically have the presentation that we give to the users, okay, very well described, okay, slide by slide. And it's mostly for you too that it can be useful. Then we have like the frequently asked questions. Okay. And so any of the questions you can have, they maybe are here. Okay. So it's just for you. It's just for you to know we have this frequently asked question thing where we basically any of the questions that we have received, we try to put them here. So basically you can get access to them. Okay. Should we wait for Robin?
Yeah.
It's good. There.
Okay, we can start.
Sounds good. Yeah, so just for you to update you guys, so as I was saying to the rest of your team, basically in the shared folder, in the folder I shared with you guys, basically have in the sales pitch side, in the sales pitch folder, in the script presentation call, we have like the detailed script of the presentation we give to the users, so they can be useful for you. But also what is can be useful for you to bear in mind is that we have this frequently asked question for basically list of the most often asked questions. And so if you have any questions, you maybe can find the answer there, and if not, you can reach out to me at any time. Okay. All right. We just try to bring together as many questions as possible. So basically, if you have questions on maybe the competitions or stuff like this, you can get access to them without us at first. All right.
All right.
Anyways. So now, if you guys don't have any questions, so let me switch to the more practical side of things. And this is generally the presentation I give to the users. Okay, the presentation I give to the users starts here. Okay, And basically, the idea of the presentation is the following. So first of all, so there to introduce the different approach to nanoparticle formulation, there are two main ones that are being used. The first one is what we call the top-down approach, and this is exactly what microfluidics, so IDEX, is doing. They start from bulk material, and you basically bring it down to PCs to form nanoparticles. All right, this is what microfluidics IDEX is doing. Okay. What we do instead and the approach we use instead, this is why it's very, very complementary, and this is why we do work with microfluidic IDEX on that, is that we use this bottom-up approach where we start from the atomic components, so the molecular components, and what we do is that we bring them together so as to form nanoparticles. Okay, this approach can be used to make pretty much any lipid-based, polymer-based, hybrids and peptides nanoparticles, okay? But overall, like as I said to you before, the range of nanoparticles you can make is very, very broad, all right? There is different methods that can be used. We talked about the top-down, and we talked about these sort of like high-pressure homogenizers like the microfluidics. In the bottom methods, there is many different ones that are available, and I'll try to cover a few for you here. How are those bottom-up methods working? It's very, very simple. Typically, the way this works is that you will start with, on the one hand, you will take your RNA, okay? You dissolve your RNA into water. On the other, you take your lipids and you dissolve them into a solvent, okay? And what you simply do is that you mix the two together, and it's by mixing the two together that basically the nanoparticle gets formed, all right? Spontaneously, so they do it by themselves. And then what you need to be doing is to carry out a filtration step, so typically to remove the excess ethanol, up until when you get your final drug product. So the process is relatively simple eventually. Now the key point to understand here is that the key step of the process is the mixing stage, all right? And this mixing stage basically is where the characteristics of the nanoparticle are being defined. And what happens during this mixing step then? During this mixing step, what happens is very, very simple. You basically start with your lipids that are fully dissolved into the ethanol, and you will start to mix it with water. The problem is that the lipids, they don't dissolve well into the water. So as you start mixing it into the water, basically the solubility of the lipids is going to decrease, and to minimize the system energy, they will come together to form nanoparticles, okay? And what is key to understand here is that the mixing speed, so the mixing conditions, have a big impact on the nanoparticle characteristics. If you take the example of the size, for instance, if you mix very quickly, you will end up with small nanoparticles. Whereas if you give them more time to grow and merge with the neighboring nanoparticles, you're gonna end up with bigger nanoparticles, okay? And so basically, the key element here is that you need to control the mixing condition, because this is what is going to allow you to control the nanoparticle characteristics, okay? And so how do you do that in practice? So the first approach, and this is what most labs start with, is that they do pipette mixing, okay? They take water, they take RNA, and they just mix the two together. It's very, very simple, okay? And basically, this is very easily accessible. You can make it in any lab, and it works. The problem is that you have no control, no repeatability, very poor encapsulation efficiency. It's very user dependent. So it's okay to do a proof of concept, but it's no more than this, okay? You cannot use it for more, all right? So this is why you have to go for more advanced mixers. The second approach, a second type of mixers that we see a lot is what we call the macrofluidic mixers, all right? In there's two main approach, T mixers or impingement jet mixers. This is what has been used to make the COVID vaccines. And the big advantage of these kind of approach is that they're basically big mixers. So you inject the liquids at very high speed and it makes the nanoparticles. Works great to make very large scale nanoparticles, but they are not suitable for R&D scale because they only work with large volumes. You cannot use them for low volumes. You can use them for low volumes. And if you remember, if you come back a few slides before, You remember here that during those first development steps, you want to work with low volumes because you want to do the screening at very low volume and the testing at low volume as well. Otherwise, it gets very expensive because RNA is very, very expensive. So basically, those methods, they work great if you want to make large volumes, but when you want to make small volumes, they are not what you want to use. And if you are in research, this is not what you want to use. And so this is why microfluidics has become the most often used technology for research is because of two things. The first one is that microfluidics allows for an excellent control over the mixing conditions because it works under laminar flow conditions, all right? The second is that it's the only technology that allows to work at small volumes. So it's only with microfluidics that you can control the mixing at microliter and milliliter scale, okay? The downside of microfluidic is that scaling up is difficult, and this is what we're working on at the moment. All right. So really, microfluidic here is just the key element to basically work at research scale. Now, how do you do mixing? How do you carry out mixing with microfluidics? Well, basically, we use two different types of mixers in our system. There is this herringbone mixer that we use in this baffle mixer. These are the two most standard mixers that are using. For RNA lipid nanoparticles, sorry for that. For RNA lipid nanoparticles, we mostly use the herringbone mixer. I would say 90% of the users, they work only with the herringbone mixer. Why is this? And basically, the idea is that this herringbone mixer is the fastest microfluidic mixer that you can find around. The way it works is very, very simple. Basically, you inject your solvent in the middle, you squeeze it between your two water phase, and as the liquid flows over these herringbone pattern chips, so there is small trenches, holes at the bottom of the chip that you see here. Basically, as the liquid flows over it, this basically leads to a folding of the liquid phase on themselves, like you see here. It really increases the surface exchange between the two liquids, and so it makes the mixing much faster, okay? This type of microfluidic mixer is very useful, mostly because it is the fastest mixer, and also because it is very easily to tune the mixing speed. Simply by tuning the injection speed to the system, you can tune the mixing speed. So that means that typically the faster you inject the fluid inside the system, the faster the liquids are, the faster the mixing, the smaller the nanoparticles. And so this is typically what you can see here in this graph. So what we did here is that we took three lipid composition, okay, and we tested them at different speed conditions, okay. The first one is that we use the total flow rate of 1 milliliter per minute, so slow flow of liquid, and you see that you obtain big nanoparticles. Now we try to increase at faster speed, so 2, 5, and it's the same if you go higher. Basically, what you see is that as you increase the speed inside the system, the nanoparticle size is going to decrease. Okay, so you can easily tune the nanoparticle characteristics simply by tuning the injection speed inside the system. Now that makes sense to you? Do you have any questions on this? Is it all clear?
I have one question about the herringbone mixer.
Yep.
So herringbone mixer is kind of well-known technique, kind of good for mixing when the flow rate is low, right? Like when the Reynolds number is below 100. But when it becomes like in a high flow rate conditions,
yep,
it is known that like baffle structure or toroidal structure is better. So I was wondering, like, I'm not sure right now because I don't know the geometry, the dimensions. So I was wondering what's going to be the Reynolds number range that you're using in this geometry.
To be very transparent, we're more in the transition regime here. We're not under turbulent flow. We're not technically under pure laminar flow in there. Okay, if you have a look at the microfluidic side of things, and mostly because like the injection speed you require in this kind of system to be efficient is usually in the milliliter per minute range, which is kind of very, very, very high for microfluidics. Okay, so you tend to work at really the boundary of what can be considered microfluidics at this stage. And this is also, and you point out a very good point here, this is also why we use this baffle mixer as well, because this baffle mixer is very complementary to the herringbone mixer. But eventually, so if you have a look at the graph on the right here, which is, I believe, very interesting for this, is that we took the exact same lipid nanoparticle composition, okay? And what we did is that we tried it with the two different mixers under different total flow rate conditions. And what you observe is that the herringbone mixer is still the fastest mixer by far, okay? But the baffle mixer is giving you a little bit more flexibility on the tunability range of the nanoparticle size. So this is why having the two is super complementary. Basically, we have the herringbone that, even though we're not purely laminar anymore, it gives us very good results in terms of PDI, so of homogeneity of the mixing, and basically gives us the smallest sizes. And at the same time, combining it with these baffle bifurcating mixers, you basically end up with a bit more flexibility on the size range you can achieve. Make sense to you?
Yeah, sounds good. Thank you.
No problem. So again, yeah, this is kind of why, in this, thanks for the introduction, it allowed me to introduce as well the baffle mixer. So what you have to bear in mind is that the baffle mixer is a very good complementary mixer to the herringbone mixer, mostly because it's slightly slower, but it gives you a bit more flexibility on the nanoparticle size you can achieve. So having the two is very, very handy. So yeah, if I have to summarize what I've been saying so far on the nanoparticle formulation side, so basically what I said is we use nanoprecipitation for lipid and polymer-based nanoparticle formulation, okay? Microfluidic mixing is key to ensure the control and homogeneity of those nanoparticle that you create. We use these two types of mixers in our system, so this herringbone and this baffle mixer, because they're very complementary. And finally, what you have to bear in mind, and this comes back to your first question, which is there is many different process parameters that affect the final nanoparticle characteristics, ranging from the formulation methods and parameters, so the type of mixer, the flow rate ratio, the total flow rate, and so on. But you have also to take into account all the chemistry around, because it also impacts the nanoparticle characteristics. So it's really a combined work between many different parameters. That makes sense to you? This was sort of the end of the science presentation. So if you have any questions on the science side, feel free to tell me, and then I'll switch more to the product. But do you have any questions on the science? Or is it all good? All good?
I have one more question. So your specification sheet indicates that Tamara exhibits like 0 sample loss, whereas Ignite shows a loss of approximately, I believe, 300 megaliters.
Yep.
So I assume this difference stems from the liquid actuation mechanisms, such that Tamara employs a pneumatic pump while Ignite uses a syringe pump.
Yep.
However, to my knowledge, all the micromixers suffers from fouling and clogging of the channel, thereby leading to sample loss. So given this, I was wondering if you have any data that directly compares Tamara and Ignite in terms of performance or reliability.
Yeah, I'll come back to this right after when I talk about the product more. I'll want to give you the introduction on the product, and then I'll give you this info. I definitely have tons of data to share with you on this, because obviously that was our first question as well. So yeah, I'll definitely cover this real quick. No question on the science aspect of things. We good? Okay, cool. So now let me explain to you how do we do it in more practical terms. So basically, what we started doing at first is, as you remember, we are microfluidicians originally. So what we did is that we started using our pressure control system that we were making with our mother company, Elverflow, and we assembled them together to form a microfluidic system for nanoparticle formulation. And this is basically what our system looked like. Why is this? Basically, the trick was, and the tricky part of it here is that you work with very small amount of liquids. We said 0.5 milliliter and you work at high flow rate, we say 5 milliliter per minute. So that means that your experiment time is very, very short. We talk about 5-6 seconds, okay? And you have to be very, very precise in a very, very short amount of time. So it's very difficult. Plus, you have a lot of dead volume. So with a standard system. So what happens is that what we realize is that with this kind of homemade system, we were able to make nice nanoparticles. The system was very flexible because you could customize it, but understanding and handling the system was very complex. And the minimum formulation volumes we could do was around 1 milliliter, which was too large to really get the full advantage of microfluidics, okay? So basically, this is the first system we made, and now we have decided to stop selling it because it is too tricky to sell and to service and to support. And this is why we've developed Tamara. We developed Tamara to really simplify the access to microfluidics. So we wanted to make it super easy to use for any non-microfluidician, okay? And we really wanted it to leverage the whole advantage of microfluidics, which is covering the microliter and milliliter volume range within the same machine, all right? And so basically, this is what how Tamara was thought and what Tamara is about, okay? Making microfluidics accessible and really leveraging the whole advantage of microfluidics. So basically, the way the Tamara system works is the following. It's very, very, very simple. We took this lipid nanoparticle pack that was working, and we put it inside the box. We made it simple to use, and we also optimized it for very low volume formulation, okay? So the system is composed of two parts. The controller on the left, the fluidic module on the right. Okay, the fluidic module, inside the fluidic module, you basically got two subcomponents. The number one subcomponent is the chip. The second subcomponent is the reservoir. All right, the microfluidic chip here is made of two designs, so the herringbone and the baffle mixer. They're very complementary, and because they're head to toe, so basically you can decide by flipping the chip if you're using one or the other. Okay, you got the reservoir. And what you simply do is that you plug in your reservoir inside the machine, you pipe it in your different lipid condition, your different lipids. You plug in the chip, you close the lid of the system, you seal it off, and then you're done. You go back to the controller, and here in the controller, sorry for this, you press on your run, and what you do here is that you select your formulation parameter. So you can select your flow rate ratio, which is the ratios of the solvent over the water over the solvent, okay? You choose your total flow rate. We discussed it. The total flow rate is what is going to basically impact the nanoparticle size, for instance. And you choose your target volume, all right? And when you input those three parameters, you can also input the chip and the solvent that you use. Basically, once you input those parameters, you press on load, you press on run, and what you then do is that you collect, what we do is that, and as you correctly pointed out, we use pressure control system here. We don't use syringe pump. And this has two main advantages. The first big advantage of pressure-driven pumps is that pressure-driven pumps is way faster than any syringe pumps. So there is no transition time. So basically there is no head and tail because of it. We managed to really go to the working condition almost instantaneously. And when you have a runtime of 5 seconds, if you have a response time that is not very, very, very fast, you basically gonna lose a lot of sample, okay, during the transition period. The second thing is that we really managed to, using pressure, really managed to wipe out everything that's in the channel out, okay, because we keep on pushing the liquid all the way through the tubing inside the chip. Unlike what unlike when you use syringe pump, because you always have some liquid left inside the tubes, inside the syringe and everything, so you have a lot of leftover, okay? So when you put the two together, this is why we have this almost zero formulation waste approach, okay? And you inject this to the system, and you basically inject this to the junction and collect this into the collection vial, okay? So this is about it. So very simple. Now, so yeah, Tamara is our first product. that we've released. And basically, we've really just tried to make Tamara not just another like Ignite-like. We really wanted to make something a bit different than what Precision Node System was doing. And so we've really designed the first system that covers all the R&D stage, because using Tamara, you can do very low volume, few hundred microliters, all the way to larger scale in vivo studies. You can do tens of milliliters with the system. It's very, very simple to use, and I believe you will see by yourself when you get the system. It is microfluidic, so you have the control and repeatability that comes with it. You have the reusable chips, and I believe you guys are gonna have questions on this. And basically, we have this zero formulation waste approach. I'll keep your question in mind regarding the zero formulation waste and the larger volumes. But first of all, do you have any questions on this? And is there anything you want me to clarify at this stage? Is it all clear? So maybe what I will do for you here is that I'll give you an introduction. So this is usually the introduction I give to the users. Okay, this introduction on the science and then on the Tamara. This is the introduction I give to to all the people I speak with. Now the main questions that usually comes is, oh, you can reuse the chips. How many times can you reuse it? This is a question that comes very, very often. And basically, to answer this question, so it's in the frequently asked questions, but here is the answer. Basically, you got only two parts that are in contact with the liquid. The first one is the reservoir. The second one is the chip. The reservoir is made out of PEEK. PEEK is a very chemically and mechanically resistant material, so you can autoclave it. You can clean it with pretty much any solvent, and you're good. Okay, the only solvent that is not good with PEEK is DMSO. Just keep this in mind. No DMSO. Aside from this, all good. The problem with the chip instead is that the chip is made of a thermoplastic, which is very, very common in microfluidics, which is called COC. And basically, this thermoplastic can be used with any polar solvent, but whenever you work with non-polar solvent, this becomes a little bit more tricky. Okay, and basically, what happens here is basically the chip. What you have to explain people is that the chip is the best of both worlds. On the one hand, the chip is cheap, okay? And because the chip is cheap, if you want to use it as a single use, because you want to avoid cross-contamination, or if you want to avoid clogging, and so to come back onto your question, we only commit on the outcome of the first run, okay? The runs after, they are on the users. If he wants to clean and reuse, this is not our problem, okay? This is the problem of the end user. Okay, and basically then, if you want to minimize the risk of clogging, basically use the chip as a single-use item. Now, what we have been doing is that we have introduced this cleaning process inside the machine. So people, if they want, they can clean and reuse the chip, but they cannot blame us. And as I say here, please note that while we allow chip cleaning, cleaning the chip for reuse may not be possible with every sample, as chip reusability can vary significantly depending on factors such as composition, concentration, and volume. So you have to bear this in mind, and it's impossible to tell how many times you're going to be reusing the chips. Nevertheless, there is this cleaning protocol that we've integrated where we first tell the people flush the system with air to remove any leftover liquids, and then flush the whole system with water and solvent. And then once you've done this, you can carry out you can just go ahead and carry out a new run. Okay, so this is typically what we see people doing. In practice, what I observe is when people are doing large volumes, okay, they will work with the chip as a single-use item. If they do low volume screening, then they will do their formulation maybe with 200-300 microliters. Then they clean, then they reuse it. And they do this, I don't know, 10, 20, 30 times. This is what we see, okay? So you really got both here. And what you have to insist is that with this, you got the best of both worlds for the users. You can do single use if you want to avoid problems and cross-contamination, but you can also clean and reuse if you feel like it, okay? So this is it. Bear in mind, okay, does it make sense to you? Okay, sounds great. So this is the people we work with. already. If you need more references, I'm very happy to share them. Maybe a couple of things that I want to share with you as we move forward. So what comes with the Tamara? Okay, so typically what we do provide with the chip is, with the system is, so provide the controller, the synthesis module, the connectors and everything. Now the two elements that are important for you to remember is that we provide, first of all, we provide 20 chips with the Tamara, 20. Okay, with every Tamara. Then people can buy extra chips if they want. Okay, and we also provide one reservoir, generally the small size reservoir. Okay, because we have two sizes of reservoirs, and this is what I wanted to insist on. Basically, we got two sizes of reservoir. Hold on. Yeah. Basically, we got two sizes of reservoirs that you see here. Okay, we got the reservoir small and we got the reservoir. Sorry, it's whatever. We have the reservoir small and we have the reservoir which is not medium. We call it large. Sorry, there is a mistake here. Let me bear in mind that it's actually a large reservoir and it's not a medium. It's large. Okay, and so basically you got the small reservoir which we use for the smallest formulation volumes. Okay, and we got the large reservoir which is for the larger volumes. Okay, so when it comes to accessible volumes, and basically going back to your question initially, what we commit on is the 0.5 to 5 milliliter range. Okay, take at up to 10 milligrams per milliliter. Okay, this is all written in the datasheet that we have, and this is what we commit on. Now we have done tons of tests up to 30 and 40 milliliters at higher concentration, and we see no problem with, for instance, the Moderna formulation. Okay, so, but the problem, and to answer your question, the problem is that it's a bit formulation dependent. There are some lipids that are a bit more sticky than others. Okay, so I cannot give you a general answer to say, oh, this is always going to be working. All right, what I can tell you though is that if you work with Moderna formulation, Pfizer formulation, we tested them and they show good results up until 30 milliliters at a higher concentration that we're supposed to be doing. All right, so technically we have a lot of margin, but in practice it's very hard to tell. This is why we sort of like back us by saying that the volume range we commit on is smaller and that we have a maximum concentration range that we can access. Make sense to you? Okay, we have data on this. I can share with you more data set on that, proving this, but basically at that stage, this is sort of like what you have to bear in mind, okay? Typically, what I still tell users is that when you work with large batches, still split it into smaller batches. This is a good habit to do overall in the process. Gives you a little bit more control if anything goes bad, okay? Another thing I wanted to show you is also regarding the control and repeatability of the system. So basically, as you see here, we did different triplicates at different formulation parameters, and you see that we are very, very repeatable, like plus or minus 5%, and we have very, very high encapsulation efficiency. Okay, so up to 95%. So it's great. Bear in mind that it remains still a bit formulation dependent. Okay. It is one of the big things that you have to bear in mind is that it's impossible to tell you, oh, this is it for everything, because it also depends a bit on the formulation that people are using. So we are doing our tests with the standard Moderna and Pfizer formulation, and eventually it's more for the people to test with their formulation if it works, and this is usually what shows the system best. Now, you mentioned also about the zero formulation waste approach. Basically, what you've seen, we have this approach where we basically wipe out all the liquid through the system. What we observe is that and this is some data comparing us with Precision Nanosystem. Okay, so the three graphs on the left are basically what you just have a look at. The yellow here is the encapsulation yield, so the recovery, if you want, and we have a recovery above 95%, whereas Precision Nanosystem basically tops at 70. Okay, so we have a much higher recovery, and so in practice we don't have 100% RNA recovery, as there is always a little bit of liquid left in the chips and so on, but we're more around 95%. Okay? And basically, the reason why we do this is, and it's basically what I showed into the video before, is that basically because we push the liquid with air, we really manage to inject 100% of it. Okay, this is especially critical for people that are working with expensive RNA material or expensive lipids, and this is really something that makes us unique, and nobody else can do that at the moment. Okay. So the chip reusability. So and this is, I come back to what I was saying. So the reusability is guaranteed, but we commit only on the first outcome. Okay. In practice, the chips are reusable 20, 30 times for small batches when you clean them well. But for larger batches, we prefer single use or splitting into smaller batches to avoid any risk of clogging, as we discussed. Okay, it's be careful. It's a little bit LNP dependent, and roughly we see that people are roughly using 40 chips per user per year. Okay, so it's kind of, it gives you also an insight of how many chips people are using. And there is a last point I insist on a lot is this dual chip design. So this is really all the commercial arguments that are using. It's not a big wow in sales, but it is very useful in practice. Bear in mind that, as you said before, the herringbone are a bit clogging prone. So one of the advantages of the baffle mixer as well is that if people are looking for a bit more scalability, those are kind of handy because they clog much less. Okay. That's it. And a last point that is really often discussed is the solvent compatibility of the chip. Okay. Basically, there is no problem. We're working with like basic solvents such as ethanol, methanol, acetone, acetonitrile, but basically working with more advanced or more complicated solvents such as like dichloromethane or toluene or this kind of stuff is not possible because of the chip compatibility. If you've already worked a lot with microfluidics, I think you know about this already, but these chips, they're designed for water and mostly polar solvent, but whenever it's too non-polar, that's just very tricky to handle. So yeah, that's it. And the ease of use, yeah, in practice, maybe a couple of elements on the ease of use. So really the system is super easy to use, and I'm really not, you will see by yourself, it's very, very easy. But being very transparent, the longest part of the process is basically the cleaning. We're looking to shorten it, but basically at the moment, basically we see that this is a bit of a tricky part because it takes like it takes usually 2 minutes. Oh.
title. Would be
I think rather than introduction, abstract would be better for this,
Yeah.
don't you think so?
yeah.
Hello,
Hi, can you hear me?
you changed the room.
Yeah, and I lost access to my. Sorry, just give me 1 second. Yeah, I basically lost. Had to change room because of it. Give me 1 second.
Okay.
That's it. So starting with the title of the article, the abstract of the article inside the box here.
Can you hear me now?
After that.
Yes,
editing,
yes.
okay.
So I have a problem
Okay.
still. Just give me 1 second.
Header component.
Okay.
Here in the edit original, on here you will have the question.
I'll come back.
저희도 회의실 지금 20분 남았거든요. 저희도 나갔다 다시 들어오죠. 지금 그 사람 나갔을 때.
오케이. 네.
네.
가셔.